times the mass of the atmosphere. You go down 33 feet in seawater, and the pressure there is 1 atmosphere. So if you multiply 33 times 270, you get something like 6,000 feet. The 60,000 feet, 5 miles or so, is the average depth of the ocean. So you would have that much mass that you would be able to heat up. Now, it takes 1,000 joules, 1,007 joules to heat 1 kilogram of air. It takes 4 times that much. It takes 4,018 joules to heat 1 kilogram of ocean. So by heating the oceans slightly, we can cool the atmosphere. If we do more of this kind of heating cooling, like this N-wave system we have in Toronto, where we're using lake water to heat and cool buildings in the downtown core of the city. The city wants to sell off its 40% ownership, but I think it should maintain it. I think it should, in fact, do more of that sort of stuff, because we can afford to heat the ocean a slight bit, and we save the atmosphere. The atmosphere is what we're really concerned about. The oceans we can adjust. It takes so long to adjust it would be almost impossible to detect the changes. Now, some of the other misconceptions about science. This one really gets me going. It's the glaciers are melting. Greenland glaciers are melting at the rate of 265 cubic kilometers every year. Now, the 365 days in a year, that's almost 1 cubic kilometer a day. That's a lot of ice that's melted. But what effect does that 265 cubic kilometers have on the ocean? It raises the ocean level by 0.7 millimeters. 0.7 millimeters every year. In 100 years, that's 70 millimeters. That's 3 inches. That much. That's what the oceans are predicted to increase at the current rate of melting. We don't even know if the melting is constant at that point, whether it's increasing or decreasing. Some years it seems to be melting at a slightly greater rate. Some years it seems to be melting at a slower rate. If all of Greenland were to melt at the rate of 265 cubic kilometers a year, it would take something like 11,500 years for it all to melt. And it would raise the sea level by 8.7 meters, which is dangerous. But that's so far from now that the societies, if we survive, would have been able to deal with it. The issue is that people are typing stuff, they're programming computers, they're doing calculations that seem to be based on some level of nonsense, that they're not doing the fundamental math to see how much energy it would take to melt those a cubic kilometer of ice. We can do that. It takes 320,000 joules of energy to melt 1 kilogram of ice. 1 kilogram is makes about 1 liter of water. So you've got in a cubic kilometer, it's 1,000 meters by 1,000 meters. That's 1,000,000 cubic meters by 1,000 meters. Sorry, it's 1,000 by 1,000 by 1,000. That's 1 times 10 to the 9 cubic meters. Now there's 1,000 liters in cubic meters. So that's 1 times 10 to the 12 kilograms of ice, approximately. It's actually 0.9 because the density of ice is 0.9 that of water. But you do the multiplication times 0.9 times 320,000, and you get the energy that's required to be put into melting 1 cubic kilometer of ice. And then you multiply that by 265, that gives you the energy that is required to melt all of that 265 cubic kilometers. That's more energy than we're using today per year. So the ice is melting faster than we're using it. So we're having some effect on it, but it's not all because of the energy we use. It's because of energy that's coming in from the sun and accumulating from that sort of aspect of it as well. So there's issues about this sort of stuff. One of the interesting papers I read was it was an interesting paper. It was picked up by one of the U.S. mainstream New York Times or Washington Post or something like that. And there was it said that they expected over the next 100 years, this person had done a computer projection that the sea level rise was going to be between 90 and 170 centimeters in 100 years. Now that's pretty big. 90 centimeters is 0.9 meters. There's 100 centimeters in a meter. There's 1 point, so that's close to 3 feet. The 1.7 or 170 centimeters, 1.7 meters. That's taller than I am. That's in 100 years. Now, we're not using energy at a rate that's possible to do that. What I suspect has happened, this person probably did the calculations and slipped the decimal point. He meant it was 90 millimeters or 170 millimeters, which is what I said, at the rate that we were talking about, that would be roughly not even 4 inches of water to something like 6 or 7 inches of water if it was on the high side. But these are the things that get published and people don't vet them properly. The people who are reviewing papers look at this stuff and they say, oh yeah, it looks good. That's fine. They don't actually do the science to verify what this person says, whether it makes sense or not. And that's part and parcel of the whole issue with some of what's happening with the climate issue. Now, this is one of my favorite things here. It's another famous Frenchman. And there are lots of them. They had good science back in the day. They still have today. But this guy's name is Le Chatelier. And he was fascinated by equations or reactions, chemical reactions that never ended. They just stayed. You had these two materials, you put them in a container, and you watch it. And there'd be this amount of this material, and this amount of that material, and they would start changing back and forth, and you could monitor. And he did. He was fascinated by this stuff. And he studied it and tried to figure out what was going on. And what he came up with was this principle. It's called Le Chatelier's principle. And what it talks about are systems that are in equilibrium. Now, equilibrium is fairly easy to understand. It's back and forth. Everything is easy. You got this system, you got that system, bouncing this way, that way. Everything is going on. You're not really doing it. But what it means is that if you have a system that is doing something and it's in a kind of an equilibrium or a pseudo-equilibrium, and you change something, then something else will have to change to accommodate it to go back to the equilibrium, to develop a new equilibrium, slightly different than the one before, but it will still be in an equilibrium. So, in climate science, we have several pseudo-equilibriums. We have the input from the sun, which changes on a daily basis, changes on a yearly basis, changes hourly, all that sort of stuff. So we never really have a really good solid equilibrium, but we do have a pseudo-equilibrium. And over the course of the year, we have so much sunlight comes in, we put in so much energy, the system kind of tries to balance this sort of thing. So what happens? Well, the temperature of the atmosphere goes up. Well, what does that do? Well, gets a little warmer. Well, what happens when air gets a little warmer? Oh, it evaporates a little more water. What does that do? That cools the oceans a little bit. Now, we've got more heat going into the atmosphere, more water evaporating. How does that affect the climate? Well, that water is lighter than the molecules of oxygen and nitrogen, which make up the bulk of the atmosphere. Water has a molecular weight of 18. Oxygen is 28, and oxygen is 32, and nitrogen is 28. So you put a molecule of water in the air, and it'll just start floating to the top of the room, and it'll get there pretty fast. So the whole issue is we evaporate water out of our oceans. It cools down the atmosphere a little bit because it takes energy to hold that water in the atmosphere. The water rises to the top of the atmosphere where, guess what? It radiates energy away. Loses energy by radiation. So it cools. And clouds form. Clouds form and they reflect more sunlight. So the atmosphere isn't heated as much by the sun because we've heated it. And so there's a balancing act that's going on. We don't have enough compute power to figure all of this stuff out. But if we did, and if the people who are making these models were able to understand these equilibria and put them in place effectively, we might get some real serious issues with how the climate is working and what our effect on it's going to be. I pointed out earlier that the combustion energy is enough to heat the atmosphere by 1.68 degrees Celsius. Let's say that's true, and that we're going to keep heating the atmosphere because we have this insatiable desire to use energy to make our lives easier, to wash our clothes, dry our hair, drive around from place to place, travel to far gone places, things like that. We're going to keep using energy, and we have to come to grips with the fact of what we're doing when we use that energy. I looked up the energy used for 2008. It was something like 5 times 10 to the 20th joules of energy, worldwide usage. Now, that energy has to go into the atmosphere because of the first law of thermodynamics, that energy has to go somewhere. It's certainly not going into the oceans because we don't have mechanisms by which it goes in very easily. So it goes into the atmosphere first, the atmosphere warms, then it will go into the oceans. But if you divide the atmospheric mass into the number of joules, you get 100 joules per kilogram of atmosphere. That works out to 1/10 of a degree Celsius temperature rise. You multiply that by 100 years, that's 10 degrees Celsius. That means by 2108, the average temperature on the Earth will be 10 degrees Celsius hotter. That's 3 times hotter than what the IPCC have been telling us. And the IPCC, and Al Gore in particular, keeps saying we need to do this cap and trade. We need to use renewable energy. We need to use solar photovoltaics and that sort of thing. That will only make things worse because photovoltaics on their own are bad news. They're only 20% efficient. They're black and they absorb 100% of the sunlight. They convert 20% of it to electricity, which ends up going back into the atmosphere, and the other 80% goes directly into heating the air around the solar panels. So if we were using solar photovoltaic energy for our energy use, we'd be heating the atmosphere at 1/2 degree a year. Fortunately, it's costly to put in solar photovoltaic systems, and hopefully the province will see the light before we get into this nonsense of paying 80 cents a kilowatt hour for stuff that doesn't do anything except heat the atmosphere. That's my issue with the photovoltaic and energy usage. Now, we talk about making clouds. And there's some interesting things about cloud formation that we don't have a historical record of. But in the 1600s, 1640 in particular to 1705, there was a time in Europe that's been referred to as the Little Ice Age. That was when the River Thames